are in chapter 11. So let me just start by motivating with an example. There's something called Benford's law. I've known about it for about an hour and 15 minutes. I read about it right before class. So it's kind of interesting though. See if you feel that way. Benford's law. What it basically is, it's kind of a current thing. It basically predicts the leading digits of lots of things in the world. Let me give you an example here. What we want to be able to do is take a bunch of leading digits and see if they match what they should be or not. How well they fit what they should be. This section is called goodness of fit. So that's what it's all about. We're going to use statistics to tell us how well a data set fits. Because nothing fits perfectly, right? This is just approximate. But the question is, how close is it? And is it so far off that we believe it can't be just luck? It can't be just random? Something fishy's going on? Or is it close enough to where we don't really think there's strong evidence for that? That's the idea. That's where statistics always comes in. All right, so how's it going to work? Well, basically, let me just give you the game plan in this section. In this section, the null hypothesis is always going to be, what is the null hypothesis always going to be? It's always going to be that the two data sets fit, meaning all categories match. And the alternative for everyone in this section, and this is 11.1, goodness of fit. 11.1, goodness of fit. The alternative hypothesis is one or more categories do not fit. So the null hypothesis is the two data sets match, or they fit, meaning all the categories are about where they should be. The alternative is, nope, one or maybe more than one categories off of where it should be. Somewhat significantly off. So with that in mind, can you tell A, B, C, D, E, or F? Look at that. F. They go up to F on their options. Which one of those is the right option? Can you tell what's being talked about there? So, probability 1 is supposed to be 30.1. That looks good. Oh, wait a minute. Yeah, no, that's good. Set 0.176 looks good. P3, 12.5, looks good. 9, etc. P9 is 0.046, looks good. And H1 is at least one of the proportions is different from the others. Yeah, that looks good to me. Right, it's not A. Why not? It's B. See what they said here? At least one of the proportions is different from the others. No, it's not about being different. It should say at least one of the proportions is not equal to the given claimed value. That's pretty picky, but that's what it should be. It's not equal to the given claimed value. All right, let's move on. That's all we need to do for number 1. Let's test it now. I'm going to move on, if you're good with that. Okay, so here's number 3. So now it's the same question. It's just going to do the rest of it now. So the company data. So here's some actual data. Let's suppose this is some actual data. Some leading digits of inter-arrival traffic times for an internet receiver. So if the time between receiving information for the internet is got these digits, 76 times. Let me make sure this data is making sense for you. This means 76 of the times are led with a 1. In other words, there's a whole bunch of, so the internet it's recording the time gap between receiving new hits on a certain site. Is that making sense? So the software is recording the times. So maybe the first one would be 1.01 second. The next would be 1.13 seconds. The next would be 4.26 seconds. The next would be 0.31 seconds. You see, all these things leading with a 1 would end up in this category. All the ones leading with the 4 would be in that category. Everything leading with the 3 would be in that category, etc. It's just recording all the times. Doesn't matter exactly how big the number is. All we care about is the leading digit. That's what Benford's law says. The leading digit 76 times was a 1, 62 times was a 2, etc. Does that make sense? That's what the program recorded. Okay. Now, you know what the test is. We just laid it out. The HO is all fit, all categories fit. H1, some do not fit. Some of the categories do not fit what they should. Benford's law. All right, here we go. Let's answer the questions. They're giving us the results right here. We'll learn how to do it on our calculator in a few minutes. But let's just suppose we've done it. There's the results from our calculator. What does it mean? There's a new test statistic. It's called chi-square. That x is that chi. It's a Greek x.
She's famous.
Chi-square. All right.
That could be your band name.
All right. So now, what do you think? Look at the p-value. Is that p low or not low? Low. Yeah, that's a low p. P is low. HO must go. Bye-bye, HO. So bye-bye to the assumption that they all fit. We're saying there's strong evidence that some do not fit. We're saying there's strong evidence that one of these categories is not, at least one, maybe more, is not coming out as it should. So what does that mean? What is our conclusion? Because the leading digits of the inter-arrival traffic times, what? Fit or do not fit? Do not fit, right? Do not fit. That's what we just determined, right? The P was low, so we rejected the null. The null is always they all fit. The alternative is some don't fit. Because the leading digits do not fit the distribution described by Benford's law, it appears that those times what? Are or are not typical? Are not. Something fishy's going on, right? There's evidence, strong evidence, right? Strong evidence that something fishy's going on. They're not typical. There is very little chance or good chance that the computer has been hacked. Good chance. Good chance the computer's been hacked. Corrective action is needed. So that's how it would indicate. It's using statistics to help alert that, hey, these numbers are funny. They're not what they should be. Isn't it weird that numbers are usually leading digits like that so often? They can use it to detect when something irregular is going on. Is that making sense on this latest statistical test? You're getting a lot of stats this semester, huh? We've learned a lot of different tests. You'll appreciate it more after it's over. That's how I always did with hard math science classes. After they were over, I was like, yeah, I learned some kind of cool stuff. In the middle, it was always torturous. All right, so that makes sense. You good there? Internet, or I mean on your thing. This was number 2, actually. That is number 2 in the homework. So that's number 2, so that's good. We're good. So here we go. So we'll do one all the way out with our calculators. The table below lists the frequency of wins for different post positions in a horse race. the different lanes or starting positions the horses are in. A post position of 1 is closest to the inside rail. So the horse that has the shortest distance to run, because the number of horses varies from year to year, only the first 10 post positions are included. Test the claim that the likelihood of winning is the same for the different post positions. Should bettors consider the post position of a horse? All right, so that's the question. So we have the 10 different positions around the racetrack, right? You know what I mean? So if you got a racetrack, and you got lane 1, lane 2, lane 3, lane 4, lane 5, etc. as they go out. So based on their post position, 18 horses won starting in position 1. 14 horses won that started in 2, 10 starting in 3, 14, 13, 6, 8, 11, 5, and 11 horses won who started out in pole position 10, post position 10. So the question is, what is the claim? Test the claim that the likelihood of winning is the same for the different positions. Is it the same? Well, I don't know. How do we do that? So if it really is the same, how many would we expect to see in this spot here? If it's really the same, meaning, it makes no difference. That's what we're wondering. Does it really make no difference where the horse starts?
Should be equal to
They should all be equal, shouldn't they?
all fit.
What's that?
They all fit. Right? They all fit in there.
Well, what fits with what? We'll get to that second here. Let's hold on. So I'm just saying, if it's really true that the post position doesn't matter, then shouldn't I see equal numbers all the way across? And of course, these are not equal numbers, but are they far enough different from equals that I think they don't fit with equality? That's the question. All right, so we got to figure that out. Now, to do that, we have to put in what we expect down here. Does that make sense? What this section, probably just have time for this one example, because this will be a little bit long, and I need to give you something on your calculator for some of you. So observed and expected. So this section is going to be a little bit of work. Observed and expected. So we're trying to see if there's a fit between what we observed, what we saw, how many horses actually did win from the different post positions, versus what we'd expect if they were equal. Right? If it was the same. So our same expectation. So how do we figure that out? What would we expect if they were all the same? Let me ask you this. If a family has, not a family, if there's 100 children born at the hospital this month, how many girls would you expect? 50. 50 girls is what you would expect. Now, how did you come up with that calculation? You took a half times 100, or 100 divided by 2. Same thing, huh? In other words, you took the probability. Well, yeah, you took 100 and you divided by 2, and you're right. So in other words, when you have a bunch of equal categories, what if? Yeah, well, let's just leave that. So we need to take the total number of horses that raced and divide it by 10 different positions, don't we? Does that make sense how we're going to figure out the expected? So we got to add all these up. So take your calculator. So what's the total number of horses? You got to add those up on your calculator and then divide by 10. So I'm getting 110, and then I take that, I take that 110 and I divide by 10, just like we took 100 children and divided by 2, because there's boy and girl. There's only 2 categories, boy and girl. So we divide by 10 different post positions. We get 11 horses per post. So we would expect that all of these would be 11. Do you see how I came up with that number?
Wait.
Yeah, so what I did, so just like to figure out how many, if 100 kids were born, how many girls you would expect, you take 100 and divide by 2, because there's just boy and girl, 2 categories. Here we have 110 total horses. If you add up all the observed horses, 110 divided by 10 different categories, we would expect 11 horses in each category. If they were all equal, right? If it made no difference where they started, their post position made no difference, then we would expect 11 winners starting from each post position. Ken?
Decimal would be just round up.
What's that?
How would decimal? Mine's 11.3.
Oh, no, just leave it exactly what it is. Yeah, if you have 11.2, just leave it 11.2
Okay.
for your data. Yeah, just leave it exactly what it is. Good question. All right, we good so far? So we have the observed and the expected. We got to put those in our calculator as L1 and L2. So L1 and L2.
Well, observed and expected?
Yeah, L1 is the observed. And L2 is the expected.
You just put that all the way across.
Is that making sense? Write the HO. What's the HO? It's always that they fit. H1 is no fit. That some category or some categories don't fit. So HO is always that they fit. H1 is that they don't fit. Does it look like they fit? Just looking at the data. Does it look like these numbers are matched up fairly close, or are they pretty far away?
Pretty far.
Some of them are pretty far, like 5. Only 5 horses won from post position number 9. Should be 11. 18 run from post position 1. That's way higher than we. It looks like it's not going to be a fit to me. Those look like they're not coming out very close to what we'd expect. There's always luck, so that's what statistics is good to determine for us now. Could that just happen by luck, or do we believe that that's beyond reasonable? That's pretty strange, and so we don't believe it's just luck. We believe there's a principle going on there. There's something happening. All right, so let's check it out. So here we go. So we need to put these into our calculator and do a goodness of fit test. So this is question number 4. So put in L1 observed, L2 expected, go to stats, and then tests. 9. Tests, and go find GOF test, chi-square GOF test. It's a chi-square GOF test. So select that, and then the degree, DF, it means degrees of freedom. It's number of categories in minus 1. So in our case, we have 10 different categories, right? There's 10 different post positions. 10 different categories, minus 1, 9. So put in degrees of freedom 9. That's always what it is, 1 less. And then calculate. And I'm getting chi-square 12.909 and a p-value 0.16 6, 6, 7, 6, blah, 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 blah. You getting that?
Not low.
Okay, so now I'm going to show for the other people that have the 83s. So this is for the TI-84 people that have that have it already on their test. So over here for the TI-83 people, you will do this. You still have it in L1, L2. That's good. You got to hit program, which is like in the middle of the top. PRGM. Hit the program button. So 83 people with me. Hit the PRGM button, and you should see the Chi GOF program. That's probably the only program you got. The one I just gave you, right?
Yep.
Select that and hit enter, and it'll just do it automatically. That's nice. You don't have to do anything. Did you get 12.909? And your p-value, this is the chi-square value, and 0.166. Beautiful. Comes out the same as the other one. Did you get that? You don't have to enter anything. This is actually easier. So what in the world does that mean? Is the p low or not?
No.
No, p is not low. So p is... Yeah, right, exactly. Come over here. So the P is 0.166. Wasn't that what it was? Yeah, 76. Not low. The P is not low. The HO does not go away. So we're sticking with the HO. And what does the HO say? It fits. So it's kind of backwards to what you might expect, huh? It's kind of weird. Gonna need to put this on your 3x5 card for sure. 4x6 card for sure.
All or 5x6, we can use
Should it be D?
So it fits. So that means we actually think these numbers fit. They fit. Now wait a minute, hold on. Why are we saying they fit? I thought we looked at them and we said they didn't fit.
I don't know.
This is the part I really hope it's coming across.
It's failed to reject. There's insufficient evidence that warrant rejection.
Is there strong or weak evidence when you go with the null? Weak. So remember, it's just like letting the person go in a court of law.
Yes.
There is some evidence that they did it, but there's just not strong enough evidence, right? There's a 16% chance that it's just lucky. There's a 16% chance that really the positions don't matter and they just came out a little different because of luck. There's too big a chance of luck. There's not strong evidence. There's some evidence, but not strong. So we got the chi-squared, the p-value. Failed to reject insufficient evidence to warrant rejection of the claim that the likelihood of winning is the same. We can't reject it. We say it fits.